Now we're going to talk about finding the domains of functions that are defined by equations. So many functions have domains of all real numbers. Anytime we've got a linear function, a quadratic function, we can just conclude that you can use anything as an input, and so our domain is all real numbers. The ones that might cause problems, if we have a fraction, we have to remember that you can't have 0 in the denominator of a fraction. And if we have a radical, that is something like a square root, cube root is also a radical, fourth root, any root is a radical. The thing we have to remember with radicals is that you cannot have a negative in the radicand of an even root. So let's actually write that down. Fractions can't have 0 in the denominator. Radicals can't have negative as the radicand. And the radicand is just the thing under the radical sign. Of an even root. So now let's do some examples. Our instructions are going to be find the domain of each function. And the first function that we're going to start with is f of x equals 5x minus 10 over x squared minus 8x plus 15. So here is our function. The radical issue doesn't apply. All I have to think about is the fraction, and all I have to think about is the domain of this fraction the denominator of this fraction cannot be 0. The numerator can be anything it wants to be, including 0, but the denominator cannot be 0. The only problems occur when the denominator is 0 So, I'll move this up a bit. So to find where the problems are, I'm going to set my denominator equal to 0. Now that will find the problems. So x squared minus 8x plus 15 equals 0. There are many ways to solve this. You could, some people always like to turn to the quadratic formula. However, this factors quite nicely as x minus 3, x minus 5. So that gives me either x minus 3 equals 0 or x minus 5 equals 0. That's from the property, the zero product property. If you have two things that multiply together to give you 0, one or the other has to be 0. Those are going to give you all the ways that that product is 0. That is a special property of 0, does not work for other numbers. So the two problem spots are 3 and 5. So 3 and 5 are not in the domain. So remember, we set it equal to 0, looking for our problem spots. The domain is everything except them. So I can write this in set builder notation as all of the x's in the set of real numbers where x is not equal to 3 and x is not equal to 5. That is one way of expressing this domain. Oh, I can't believe I wrote that out without you being on camera. So let me go over that again. The domain is all of the x's that are real numbers where x is not equal to 3 and x is not equal to 5. So that is all of my real numbers, taking those two numbers out. Another way of expressing that is in interval notation. Well, I can't express it as a single interval, but I can always start about thinking, coming from the left. From negative infinity, the first problem I have is at 3. So I go from negative infinity to 3, open parentheses, because my 3 is not included in this domain. And then I'm going to union that. My next problem spot is 5. Everything in between 3 and 5 is included. Notice that I'm using parentheses to mark my ends of my interval because these are not included in the domain. And then everything to the right of 5 is included. So that's 5 to infinity. So there's the domain of our first function. Okay, our next function that we're finding the domain for is g of x equals the 8th root of x plus 10. So here we have a radical, and it's an even root. That means the radicand must be positive or 0. It cannot be negative. Problems occur when the radicand is negative. And when we're talking about graphing these things, we're really living in a realm of real numbers. We do know that imaginary numbers exist, but as far as the real domain of this function, we have to have a positive or a non-negative radicand, positive or 0. Actually, let's write that. So x plus 10 must be positive or 0. So set up the inequality. X plus 10 is greater than or equal to 0. I want to point out a difference between this problem and number 1. In number 1, we were looking for the problems, so we set the denominator equal to 0 to tell us where the problems were, to tell us everything that it could not be. Here we are looking for everything that it could be. I set this up to what needs to be true. And so then when I solve this, my solution set will be all of the numbers that are in the domain, as opposed to in the first problem where we found all the numbers that were not in the domain. So this is a simple inequality to solve. I subtract 10 from both sides. I get x is greater than or equal to negative 10. So the domain is, all of the real numbers, x is a real number, where x is greater than or equal to negative 10. In interval notation, this is, well, this is something that I can express as a single interval. Negative 10 to infinity, everything that's greater than or equal to negative 10. Notice that I did include the square bracket because of the or equal to. All right, next we're going to have another radical function. We'll call this h of x. And that is the cube root of x squared minus 5x plus 2. Make my bar go all the way across there. And let's actually get crazy, and we'll even say plus x on the outside. So that plus x actually doesn't affect anything. It doesn't add any restrictions. I do have a radical here, but look at this. I've got an odd root, and the only problems occur with even roots. So since no problems occur, with odd roots, this function has a domain of all real numbers. Well, that's our symbol for the set of real numbers. And if you want to put it in interval notation, this is the interval from negative infinity to positive infinity.